In this video, I would like to teach how to do impedance matching. Okay, what is impedance matching? Impedance matching is a method to match the transmission line with the load. Okay, why we want to match the line with the load? Because we want to avoid a reflection of the signal. Meaning, if we can achieve this, means the standing wave ratio equal to 1. So how to achieve this? We have to make sure that the input impedance at that location where we insert the matching component will give a total of Z0, means the input impedance is equal to the characteristic impedance, or in terms of admittance, input admittance equal to 1 over characteristic impedance. So to solve this, to do the matching, impedance matching, we can either use capacitor or short circuit stub. There are two means, and we need two Smith chart. Okay, the steps to do this: first, we need to find the location on the transmission line to insert the matching component. Okay, so to do this, we need to find on the, using a Smith chart, where is the location that will give you normalized input admittance equal to 1. Why equal to 1? Because this is where the input admittance equal to 1 over Z0. Okay, and at that point you will have some imaginary part, either positive or negative. So because we want to achieve at the end, we only want to have input admittance equal to 1 over Z0, and in other words, the normalized input admittance equal to 1. We don't want to have imaginary part, so we need to do the second step to remove the imaginary part. So we need to use another Smith chart to find the stable component value. If we use capacitor as the matching component, we need to find the capacitance. This is like question number 8 in the tutorial. Okay, if we use short circuit stub, we need to find the length of short circuit stub so that we can cancel the imaginary part. Okay, let's look at how we can do this using example number 5 in the lecture slide. In the lecture slide, you are given 50 ohm transmission line, and you want to match the line with a load of 15 plus J21 ohm, and in the question you are asked to use 100 ohm short shunt stub. Okay, so this 100 ohm is the characteristic impedance of the short circuit. This 50 ohm is the characteristic impedance of the transmission line. Okay, please bear in mind there are two different value of characteristic impedance. Okay, what you want to do is actually in drawing, okay, you have a load, okay, and you have a line. These two are not matched. You have a different value for load and line, so you want to insert a short circuit. And what you want to know now is where to insert the short circuit, okay, and how long is the short circuit stop. Okay, so to do this, we need to use two Smith chart. The first Smith chart is to find D, where to insert the short circuit. So how to find where? You have to find on the Smith chart where the input admittance has real part equal to 1. Okay, and then you read what is the value of the imaginary part. From the imaginary part, you can find what is the length, because the length of the short circuit stub will indicate how much that you have to add or minus so that you can cancel the imaginary part. So let's look at how we solve question number 5. So as usual, find the normalized load impedance. 15 plus J21 divided by 50. So the normalized load impedance 0.3 plus J 0.42. Locate that point on the Smith chart. 0.3 plus J 0.42. It is here. So label. And as usual, we draw a straight line passing through ZL. Okay. In solving impedance matching, you have to use the Smith chart as admittance chart. So you need to find YL. So to find YL, you need to draw constant SWR circle. Okay, so this is your constant SWR circle, and your YL is here. So as I mentioned just now, what you want to find is the distance from the load. So now your load is here. So read the location of the load. In this case, from my drawing, it is, this is 0.31, this is 0.32, so it is 0.319 lambda on the wavelength to generator scale. Okay, your drawing might be a little bit off from mine, but it doesn't matter. I will, in the exam or in the test, I will mark based on your drawing. So let's say your line is passing through 0.318, you just write your value as 0.318. So plus minus value will be accepted. Depends on your drawing. So try to draw as accurate as possible. So now this is the location of your load. Okay, YL. As I mentioned just now, to find D, what you need to find is the distance from the load to a point where Y in equal to 1. Y in equal to 1, here, this is 1. Okay, the resistance value equal to 1 is along this line, along this circle. So this is location where Y in equal to 1. Okay, and you see the value is Y in equal to 1 plus J 1.5. Okay, how do you read 1.5? You trace the reactance circle and find the value is 1.5. So draw a straight line passing through that. You can see the value here on wavelengths to its generator is around 0.176. Okay, so now what you want to find is the distance from the load, to the input admittance point. So you need to find the distance from here to here. Okay, as I mentioned before, from the load you must always use clockwise direction to move towards input. Okay, so Y must be the distance between Y to Y, mean YL to Y in. Don't be confused with Z, because now you are dealing with admittance. Okay, now you know the location of the load is at 0.319. The location of the input is 0.176 lambda. So you want to know the distance. So use your logical, I mean, this is like a ruler, right? Starting from here. Okay, I like to use both scale to find the distance. Okay, so to find the distance between the 2 points, from here to here, it is 0.176 lambda, and from here to here, okay, don't be confused. This 0.319 is from here, around here until here, because that is the scale WTG. So if you want to know the remaining here, you need to add with 0.5 minus 0.319 lambda. Why you need to have 0.5? Because one round is 0.5, and this 0.319 lambda is from here to here. So to know this from here to here, just use the whole distance for one round minus this to get this. That's why you have this 0.5. You can use this, or you can use different scale here. One is WTG, this is WTG. Another one is WTL. So here at this location is also equal to 0.180 1 lambda on WTL. So because WTL increase from here to here, meaning we know straight away from here to here is 0.8181. So the distance, if you use both scale, you just add 0.176 lambda plus 0.181 lambda. Okay, so you will get 0.357, right? 0.357 lambda. So this is where the location where you want to insert the short circuit stub. Okay, this location, meaning this D here, this, right? So let's say in the question we give you the value of lambda, or we give you the value of the speed and frequency. You can find lambda, then you have to find the distance in meter. But this one, in this question, you don't give you lambda, the value for lambda, so you can leave the answer in terms of lambda. Okay, so we have done the first part to find the location. Next, we want to find what is the length. Okay, as I mentioned just now, the first step, find the location. We have done that. So now we want to find the suitable component. Suitable component in this case, because we use short circuit stub, we need to find the line. So how to find the line? So as I mentioned just now, what we want to achieve is we want to have y in equal to 1. We don't want to have this imaginary part. So we want to cancel one susceptance, capacitive susceptance of 1.5. And remember, this is a normalized value. Okay. So we need to use another Smith chart. So before we use the Smith chart, we need to find what is the effective susceptance that we want to cancel. Okay, so the normalized value is 1.5. So 1.5, we need to denormalize it. Okay. So the y in at that point is equal to the normalized value. Denormalized means we have to multiply with y naught. In other words, we have to divide by z naught. So we divide with 50 ohm. So since we know this, the normalized is 1 plus j 1.5. So 1 divided by 50 plus j 1.5 divided by 50. Okay, so we have 1 over 50 plus j 0.03. So now the important part is here, the 0.03. So this is the actual input admittance that we want to cancel by using the short circuit stub. So to do that, okay, so we want to insert a stub so that it cancel the plus j 0.03. In other words, we want to insert a stub so that the admittance of the stub will give you negative j 0.03. Okay, as mentioned just now, we calculated the input admittance at that location at D at 0.357 lambda just now is 0.03. So we need to cancel this. That's why we need to insert a stub to give negative j 0.03. Okay, so this is actual value. So to find the location on the Smith chart, you have to normalize it. Normalize means you divide by y naught. In other words, you are multiplying by z naught, multiplying by 50 ohm. So the value on the Smith chart is negative J3. So the admittance of the stub that we want to introduce is negative J3, and we know this is a short circuit stub. So where is the, we want to know the line. Okay, so now your load in this case is a short circuit load, because you're using short circuit stub. Your short circuit load location on the Smith chart, where the admittance is short circuit, is this point. Okay, this is location where the, what you call it, admittance is short circuit, this point. Okay, and then where is negative J3? So here this is the negative J3, so this is the location of negative J3. Okay, why this point? You see resistance value starting from 0.1. So all the point along this line, the outermost part of the circle is having resistance equal to 0. So that's why it's on the border here. It's 0 minus J3, this point. Okay, so this is where you have the input admittance equal to negative J3. Okay, so what we want to find is the length of the short circuit. So this is where introduce negative J3 at this point. Okay, and the load for the short circuit is the admittance is infinite, isn't it? Means ZL equal to 0 and YL is equal to infinite, which is this location. So this is the location of the load for the short circuit, not the load of the line. This is the short circuit admittance point, this one. So the length of the short circuit stub will be this, from here to here. Okay, so what is the length? So from the Smith chart, L, find L. So you read the value here. This is 0.3, this is 0.31. So this is 0.301. Okay, this location on wavelength towards generator scale, and here the location is 0.25. Okay, so the distance, the length will be, this is L, this is L. Okay, so the length L will be 0.301 from the Smith chart. 0.301 minus 0.25. So it is 0.051 lambda. Okay, so this is the length of the short circuit stub, so that the line and the load is matched. Okay, one thing that I forgot to highlight just now. How do we get this 0.3 negative J3? Okay, right, be careful with this one. Okay, this Z naught is equal to 100. This is the characteristic impedance of the short circuit stub. Okay, so in the question just now, you are given 100 ohm short circuit stub. Okay, different from the characteristic impedance of the transmission line. So that's why you get negative J3. Okay, so be careful this one. This is not the characteristic impedance of the transmission line. This is characteristic impedance of the short circuit stub. Okay, so we have solved the impedance matching problem, where we find the solution D, the distance where to insert the short circuit stub, equal to 0.357 lambda, and the length of the short skirt stub equal to 0.051. So your answer can be plus or minus. Sometimes if you refer to the lecture slide, so you see the answer is 0.358. Actually depends on your drawing. Maybe like my drawing is now, I got 0.357 lambda. So it can be plus minus. Right, so I hope you understand how to solve an impedance matching problem.